So we have all heard of, because it's the most famous thing in all of science, you can probably get elementary kids to write this down. You guys know this. Oops, that's why I did such a curvy E there. You guys have all seen this before. Never in your life. Never in your life. It doesn't make any sense. That's silly. It's not what, like, small children should recite. It's like, what science-y? They're like, this stuff. Or like, who's Einstein? Equals MC squared stuff. But having a meaning to this really throws your concept of reality out the window a little bit. It's kind of weird. Basically, every description of the world kind of is at best an approximation. And so, just like you said with the Galilean transformations, basically saying, if we assume the speed of light is infinite, that works for, driving around town. The speed of light can be essentially infinite, and it won't really mess up anything to any degree. But when we start talking about causal space, then it's a problem, right? But in regular life, do we think the speed of light is infinite? Yeah, it's big enough that it's essentially infinite, that we don't need to worry about it. It doesn't affect our day. It's 300,000 kilometers a second. That's really fast. So, coming into the last lesson, when an object is accelerated from rest to a speed, the mass of the object increases. Right? So, is a fast-moving object, since it has more mass, because relativity, then it obviously also has more energy.
Is that M as in M naught at rest?
Not anymore, because we are now moving. It was. And no, it never is.
No? Okay.
No. Because M is mass. And M naught is specifically a special case of mass that isn't moving. It's specifically your rest mass, measured in an inertial frame at rest with the person doing the measurements.
Right.
So, an increase in energy. So a moving object has more energy than a not moving object.
No way.
And since a gain and loss in mass can be regarded as a gain and loss in energy, mass and energy are equivalent. So as we did with relativity, a moving object has more energy than a stationary object, but a moving object has more mass than a stationary object. Which is weird. So we're going to use our mass increase formula here, according to the special theory of relativity. A total energy of an object moving with a speed is defined as the product of the relativistic mass of the object and the speed of light squared. So we know this one, right? We know E equals mc squared. Now, m, without anything there, is relativistic mass. I did not give myself enough room to write that in. Let's try again. It's relativistic. So we can also write our energy in terms of rest mass. So using rest mass, we have to use the transformation. So we get m naught over 1 minus v squared over c squared. And c squared there. So this is also true. This is also your equivalence of energy. Now, the total energy of an object, what happens when its speed is 0? Is the total energy 0? If its speed is 0?
Yes.
No. So, it does not vanish. right? Because rest energy can be a thing, right? If V equals 0, that whole equation doesn't turn into 0, right? If I have rest energy, or E naught, which is a rest energy, a no velocity. It's what the 0 means when we're doing all of these things. It just means 0. So in this case, relativity is all about velocity. That's your rest mass and c squared. So rest energy, just an object by itself, is its rest mass and c squared. Any questions so far? Still feel it's just basically just rewriting transformations over and over again. Okay. When an object is accelerated from rest to a speed, an object acquires kinetic energy. You're like, yes, something I understand and agree with. If I make something go from rest to speed, it has gained kinetic energy. Excellent. So it has kinetic energy and its rest energy. So the kinetic energy of the object is the difference between its total energy and its rest energy. Which makes sense, correct? That feels good. It's its speed energy minus its stop energy is its kinetic energy. That seem good?
Yeah.
That like this is the classical kind of kinetic energy transformations where like how much kinetic energy do you have when you're stopped? None. And so you can add the kinetic energy. So the total energy minus the rest energy is your kinetic energy. So we're going to do a little formula here. Kinetic energy, which I like to write as EK, is equal to your total energy minus your rest energy. Now, I wrote it hard on the left side for a reason, because we're going to put the two formulas that we did above in as well. So total energy is equal to m naught c squared over 1 square root of 1 minus v squared over c squared. So that's my total energy, and we're going to subtract the rest energy. Now that's kind of ugly. Let's factor out one of these. We can get m naught, clean that up, 0, m naught c squared, all bracket, 1 over 1 minus v squared over c squared, rooted, minus 1. It's kind of a ridiculous looking formula, but we basically have this factor here. It's basically we have rest energy and this factor that has our speed in it. So it's a good formula. I don't think it's on your sheet because, again, the sheet was last year's sheet. We started there. We're going to obviously are adding to it as we go. So since mass and energy are the same, or equivalent, in other words, can be changed back and forth, any change in one causes a change in the other. So we can write a kind of simplified formula here. The change in energy is equal to the change in mass times c squared. So that's probably the most accurate form of the E equals mc squared. It's just the change in is the most common form of this. So it's one of those things that we often leave out of formulas because they're kind of inherent. We don't often put the delta symbol in front of time, even though all times are intervals. so we can kind of just assume them. All distances are all changes in position. We just kind of leave them off as assumptions. So often these delta symbols or change in symbols are often left out because of just convenience and laziness. I should probably write down what I said. Yeah, it's changing the other. I said it out loud, and I don't know why this didn't fill it in automatically. This should be a voice-activated note-taking system. That would be much more convenient if I did this via voice and not...
Great to just have our tangents on the paper.
Yeah, pretty easy. Voice-activated notes.
I'd probably study my notes more.
If they were voice-activated?
Yeah, if they recorded the whole lesson.
Well,
All of it's entertaining.
Oh. All right, let's try an example problem. We've got a proton. Everyone knows proton's rest mass is 1.67 times 10 to the negative 27th kilogram, which is incredibly small. Accelerated from rest to a speed of really fast, 8.7 times 10 to the 7th meters per second in a particle accelerator. What is the rest energy of the proton? Yes. Math already?
What is c squared?
No.
No, what is c?
Oh, c is the speed of light. 3 times 10 to the 8th meters per second.
I didn't know there's what power.
Yeah, it's on the formula sheet if you forget. Rest energy is E naught. Oh, not sigma. Been too much stuff with my math 10s. E naught, rest energy. So that's m naught c squared. And so we get 1.67 times 10 to the minus 27th multiplied by c squared, 3 times 10 to the 8th meters per second, all squared. And we get this kind of small number. 10 to the minus 10, which is going to be 1.5 to our... Printing fell apart here. Minus 10, and it's joules in energy. That was kind of easy, right? Okay, slightly more annoying, just more calculator work. What's the total energy of this proton in this situation? We have to use its speed. So it's probably a great idea for us to try to find the c. So what? Yeah, is it better? Okay. What's the c speed? Right? The percentage, basically, of the speed of light. So instead of saying it's going 8.7 times 10 to the 10th meters per second, what is that in terms of c? Right? So we're going to do a quick percentage calculation here to start us off here. So we're going to go 8.7 times 10 to the 7th, divide by 3.0 times 10 to the 8th, and we can get our speed in c. Well, it should be 0 point something, right? It's not going to be 1 point something. That would be bad.
Is it low?
Oh, not negative 7. Oh my gosh, it's not negative 7. It's positive 7.
Is it low?
It shouldn't be that low. Did you use negative 7? Because I made a mistake. It's definitely not negative 7. 8.7. Yeah, 0.29 sounds good. E minus 7. No, minus 7. I keep doing that. Why do I want to do minus 7 divided by 3.08? Yeah. 0.29 c. So instead of writing it with all the significant digits, we can use 0.29 c and save ourselves a little bit of work here. Because total energy has a Lorentz transformation in it. Total energy is rest mass c squared over 1 minus v squared over c squared in a square root symbol. And so, Hmm?
You do all the math, and then you're like, oh, that's not very significant.
Correct.
Protons don't carry a lot of kinetic energy.
That's because they're small.
Turns out.
Turns out, not a lot of kinetic energy in a proton. Who knew? Not in terms of joules, anyways. What are we doing here? 1.6 times 10, 1.67 times 10. I will slow down my writing. Yeah, that'll do it. It's a little messy, but that's where we get. And it's 1.5705, 10 to the minus 10 joules, or roughly 1.6 times 10 to the minus 10 joules. So, roughly the same, right? Not much. And the reason it's not much is basically why we can get, that's why we don't have to teach you what relativity is on the first day of Physics 11, because these are small changes. They can become more significant, but only at ridiculous speeds, or more appropriately, ludicrous speed. Okay, so kinetic energy is my difference of these two, right? We use this formula. We've got the kinetic energy. Instead of trying to figure out something massive, we've got total minus rest. And so we get 1.5705 times 10 to the minus 10 minus 1.503 times 10 to the minus 10. And I get, or what's going to be 6.75 times 10 to the minus 12 joules. Yeah, we're getting real small, right? What is that, a trillionth of a joule?
Won't that round to one sig big though?
Because it's a subtraction?
Because it's subtraction.
Well, it'll round to 2. We'll call it 2. Yeah, we call everything 2 in this book. So yeah, it's a pretty small. So what's my percentage error? If I did classical kinetic energy. So if I ignored fancy relativity, even though this thing's going pretty fast, how badly would my calculation be if I did it with without considering what relativity is? So first we have to figure out what is the kinetic energy normally, which is half m naught v squared. You can just figure out that speed and figure out what that number would be. 0.5, 1.67 times 10 to the minus 27, and then 8.7 times 10 to the minus, why did I do that? Just regular 7 squared. So regular kinetic energy. Ignoring what relativity is and just saying, hey, this particle's going pretty fast. What's its kinetic energy?
It's not too far off.
It's not bad, though, right? It's 6.32 times 10 to the minus 12. It's not bad. So to get a percent, right?
So 93% similar.
Percent error, we do it the other way around. So we go 6.32 times 10 to the minus 12 minus 6.75 times 10 to the minus 12. Probably could have ignored the times 10 to the minus 12s, though. 6.75. That's quick math on that. Don't need all the... If you're typing into calculators, don't use the exponential notation. It cancels out. So just type the numbers. 6.32 minus 6.75 divided by 6.75. 0.06? 4, I guess? So it's negative 6.4%. So, yeah, in most cases, we can pretty much get away with this, can't we? If we ignored all that relativity math, we'd be 6% off. Engineering would probably say, that's totally fine.